presentation. Good morning, everyone. I'm here today to present a constitutive model able to simulate the behavior of FRCM. What is FRCM? FRCM is a new composite material, and it stands for fabric reinforced cementitious matrix. What is this composite material? It's composed by 2 or more layers of mortar, cementitious mortar, that is generally enriched with AR glass filaments and polymers. And in the middle of these layers of mortar, there's a fiber grid that is made of carbon or glass or other synthetic fibers like PBO. This material is used to retrofit and to strengthen existing structures like concrete structures or masonry structures. So, the model. Since this is a new composite material, many authors in recent past have conducted experimental tests to determine the mechanical property and behavior of the material itself. So, like shear tests to determine the bond between the fabric and the mortar and the substrate, or tensile tests to determine the whole behavior of the material. Other tests on, for example, beams retrofitted with this material. So, the aim of this work is focused on the numerical simulations of this material, and in particular of the development of a macroscopic constitutive model that is able to simulate the behavior of this material, and that could be implemented into a nonlinear finite element procedure. And the fitness of this constitutive model was verified through comparison with experimental data that can be found in technical literature, in particular relative to FRCM tension ties. So the model. According to the model, a FRCM membrane element subjected to plane stress state is considered. And the model belongs to the smeared model family, and according to it, any point of this material could be cracked or uncracked. If it's considered uncracked, only the elastic modulus and Poisson coefficient of mortars and fibers governs the behavior of the material at that point, while if it's considered cracked, other contributions have to be taken into account, like the bridging of the inner so of the mortar itself, or the initial stiffening that the fiber grid exerts over the mortar. The model has a modular framework, so each contribution is separately modeled and modeled with a semi-realistic empirical law. The model itself was translated into a formal language, and that can be used with Abacus in a user subroutine. So, the 2 fundamental phases of the model. So, a generic point can be cracked or uncracked. It's considered uncracked if the tensile stress in that point is lower than the tensile strength of the mortar. So, the hypothesis of perfect bond is still valid, and the strain at that point of the mortar is equal to the strain of the fiber grid that is equal to the total strain. So, the 2 stiffness matrices, one of the mortar and one of the fiber grid, can be written in the classic way, and the stress field is the sum of the stress in the mortar and the stress in the fiber grid. While when in the point the tensile stress is higher than the tensile strength of the mortar, the material in that point is considered cracked. So the hypothesis of perfect bond is no longer valid, and the strain in that point is the sum of the strain of the mortar between 2 adjacent crack, so these terms, and the strain in the fracture zone. So the strain of the mortar between 2 adjacent crack can be calculated with the same stiffness matrices that we have already seen in the last slide, while the strain in the fracture zone is governed by this matrix, that is a crack stiffness matrix that can be evaluated after some passage, and is due to the contribution contribution of the mortar and of the fiber grid in the fractal zone. So after some mathematical passing, we can reach this stress field that can be written in this way. So these two contributions, so the mortar in the fractal zone and the fiber grid in the fractal zone, we have to evaluate these two contributions. The first one, so we are in the fractal zone, and we have to evaluate the matrix that is given from the mortar. So we modeled this matrix by two. We construct this matrix by two bridging coefficients. A bridging coefficient that is due to the plane mortar, and a bridging coefficient that is due to the dispersed filaments and polymers that are dispersed in the mortar. And this is in accordance with the model that he proposed in 1992. In fact, the plain mortar have a tensile softening behavior after first crack, so we evaluate this bridging law with the Ishiguro bridging law that was proposed in 2007, and then we can reach this contribution, this bridging contribution, while the dispersed filaments in the mortar exerts a fiber bridging and a fiber process effects over the crack in the mortar, and so we can evaluate this contribution. So we can write this matrix, this crack stiffness matrix for the mortar in the local reference system of the crack. While the fibers, so for the fibers, this is the crack stiffness matrix written in the local reference system of the fiber grid itself. And then, as you can see, the elastic modulus of the fiber grid is multiplied by a tension stiffening coefficient. Tension stiffening coefficient, that is the ratio between the deformation, the strain of the fiber grid, and the total strain in the fractal zone. This contribution, so the strain of the fiber grid, can be evaluated after solving the classical second order bond slip equation. For the bond law, we took the model code law after calibrated these parameters on the basis of experimental shear tests. So we have these two stiffness matrices of the mortar and of the fiber grid in the local reference system. We translated them back in the global reference system, and then we can obtain the crack stiffness matrix. So to validate the effectiveness of this constitutive model, we made some comparisons with experimental tests. The campaign was conducted by Carrozza and Poggi in Milan, and the specimens were rectangular bonds that at their ends were clamped in a machine, with reinforced fiber plates glued at their end, and so they were tension ties. And this type of clamping system allows investigation the whole behavior of the material up to the failure. Two groups of specimens were investigated, one of them with the PBO fibers and the other one with the carbon fibers. The simulation, so the model was implemented into Fortran language and implemented into a user sub which is used with Abacus. The mesh is there, so we modeled on behalf of the specimen taking advantage of the symmetry, putting appropriate constraint. We chose a membrane element with reduced integration with 8 nodes, and in the specimen control, in this table we see the mechanical characteristics of the fiber grids and of the mortars. Some mechanical characteristics were declared by the producer, other ones are calculated from the authors, and other ones are obtained from technical literature correlation. So the results. In these two graphs, you can see in these graphs the result of the group of specimens for carbon fibers net, while in this one the results for the group of specimens with the fiber net made of PBO. In this graph, you can see 3 dots lines. So the lower one represents the minimum of the envelope of all experimental data, the higher one represents the maximum, and the blue dot line represents the average values of the experimental data. The dashed line represents the numerical results, so we can say that there's a good agreement between the numerical and experimental results. So in conclusion, a nonlinear constitutive model was presented, and the procedure was verified through comparison with experimental data, and further developments could be the extension of the model, taking account early third shrinkage, and then the model of reinforcement with beam strength and retrofitted with this material. Thank you for the attention.